we're going to kind of take the last step before we get into circuitry and talk about the last kind of piece of the puzzle. We've talked about voltage, the pressure behind, and the potential difference. We've talked about the flow rate, how many coulombs per second are passing by, thinking that as gallons per minute if you equated that to our analogy of water. And then resistance, talking about how much internal friction those charges are going to face as they go through, and putting it all together with Ohm's law, and that's V equals IR. Most equations are all going to, when we're dealing with electricity, are all going to be based around in some form or fashion using substitution or using this, um, the V equals IR, the Ohm's law. We're dealing with units so far in voltage of volts. That's your potential difference between two spots. Now you'll start hearing us call it voltage as opposed to potential difference. Where that comes into play, or why that changes, if you remember, we were looking at the difference. If the difference was 10 volts on one side, 5 volts on the other side, what we cared about that the difference was 5 volts. What we're going to now assume is that we're using zero as our reference, kind of like the roller coaster idea. The lowest spot was our reference, even though it may be above the ground. We're now going to assume the lowest spot is what we call the ground in electrical land, and use it as zero. So when you hear voltage, all we're saying is we're assuming our reference point of zero. So in that case, we just say the voltage is 5, knowing the difference is 5, and it could be 15 and 10. It could be 20 and 15. But all we care about is that difference in that ratio. All right. We're going to start talking about power. If you remember back from when we discussed power back in Newtonian physics, it was the ability to do work. And it was measured in watts, and we were talking about the amount of joules per second, okay, the amount of work that you could do in a certain amount of time. The same thing is going to hold true. A lot of times, like when you go buy a light bulb, the old school screw-in light bulbs, you're like, I need a 60-watt light bulb. What that's really saying is that light bulb has the ability to convert 60 joules of electrical energy per second and turn it into light. So that's what you're talking about when you say, go grab me a 60-watt light bulb. Now, what does that mean? And how do we calculate that? And that's going to lead us into calculating, per se, how much, is that light bulb going to actually cost you? You look at all these new light technologies, how much are you actually saving? Because the newer technologies are a lot more expensive to buy up front. Are you going to actually make a difference in your money or the cost? How much is it going to cost to charge your cell phone? When you see that 95% efficient or that star energy rating, what does that all mean? And that's all based around these watts. Also, you're going to see it calculating your electric bill in something called kilowatt hours. And you're going to do a worksheet, kind of a little bit of a investigation of how your electric bill is actually calculated. All right. So power, putting charges to work. The more movement of a charge from the terminal to terminal, okay, we're talking about the electrical energy, but we're also looking about the rate at which it's being transformed into what we call useful form. So if we go back to that example of a 60-watt light bulb, it's looking about the amount of energy per second that's being converted, in this case, from electrical to the usable, which in our case is light, with using that light bulb. Now, most of the time, electrical device is going to have some form of resistance, some form of a load. A lot of times you'll hear it called. That could be a light bulb, that could be a buzzer, that could be your refrigerator, that could be your cell phone. It has to have some form of resistance, because if not, those charges are just going to go full bore, and they're going to go so fast, cause so much heat because they're moving so fast, and potentially cause a fire. And that's what you talk about with a short circuit. A short circuit is just a term, and you'll see that in a lab simulation next week when you start building circuits. If there's no resistance, it's bypassing any of these loads. It has nowhere to distribute that energy. And so that energy is getting distributed right back into the wall, or right back into, say, your battery, and producing a lot of heat and potentially a fire. So we have a load on this device, and it's going to convert this electrical energy into some form of other energy. Now, remember, total energy is going to remain the same. So that electrical energy could be converted in the case of a light bulb into mostly light and heat. It could be a speaker, so that electrical energy is getting converted into kinetic energy, the motion, acoustical, and so forth. So we're talking about at its most fundamental point that an electrical circuit, whether it's in the wall, whether it's in your computer board, it is taking electrical energy and transforming it into something else. Okay? And it's being transformed in this load. Okay. A load, when we talk about it, again, it's not real important what that load is, but that's your refrigerator, that's your washing machine, that's your cell phone. In our equations, how we treat that is that's just your resistance. That's the thing that is applying or creating that resistance. And that resistance is taking some of that energy, electrical energy, and converting it into something else, whatever that might be. The power is the rate at which that electrical energy is supplied to the circuit and consumed by the load. So again, the 60-watt light bulb is taking 60 joules per second. Remember, watt is joules per second, and being converted into something else. In a light bulb, most of it's light, a little bit of it is going to be heat. Now, in a heating element, say like in a toaster, all that electrical energy is being converted straight into heat. So you're going to have a lot of resistance there. So again, when we talked about Newtonian, it was always talking about amount of work, which was our force times distance, divided by in the rate, so divided by time, joules per second. The same, or a watt. The same things can be true. We now just kind of talk about it a little differently and talk about the energy being consumed, or I like to think about it being transformed by the load as far as being, instead of being consumed, it's a little misleading that it's being lost. Okay, so the big thing here is the power is referred to as the rate that that energy change is occurring. Whether it's positive or negative, for our purposes right now, it's not real important. If you flip the terminals, the positive, negative are just going to flip flop. And just as a reminder, your 1 watt is a joule per second. So a 60-watt light bulb is taking 60 joules of electrical energy and converting it every second. A 100-watt, 20-watt light bulb, 120 joules per second. Now, looking at power, as far as an electrical standpoint, it's still going to be the amount of work, but we have to calculate work a little bit differently than we did with Newtonian. If you think about force, distance and time is speed, so it's equated to current in our electrical land. And the force, you want to think about it as the pressure, or in this case, the voltage. So you're going to see those things at play looking at the current and the voltage. So just kind of doing a little conversion. Again, these derivations are not for you to memorize or to be able to duplicate. It's just to show you that these equations are not made up or pulled out of thin air. So just going back to Newtonian world, power is work divided by time, which is our, if you think about our work energy theorem, it's the change in potential energy divided by time. Voltage, if you remember, is your change in potential energy per charge. I'm just going to rearrange it. So I'm rearranging this one, solving it for change in potential energy. And then I do a little substitution. Okay. And I end up with Q times the change in potential divided by time. Now, the rate that charge is moving, Q divided by T, is your current. So that's how we end up with our electric power equation. A lot of times you hear it called PIV, P equals IV. Okay. Power is going to equal your current times your voltage, or your potential difference. Now, with this, there are a couple of other different forms, and we'll look at these next chapter. But remember, you have I and V. So if you're dealing with R, you don't see that anywhere in there, the resistance. So remember, you can always use and go back and in conjunction with this, use Ohm's law. Now, if you want to talk about and kind of combine it, I can eliminate voltage. I can sub in here. So if I take this and sub in, you end up with P equals I times R. So I squared R. That's the rate that the power or the energy is being consumed. Okay. But this is your main power equation. And again, you can always find missing pieces and parts using going back to Ohm's law. So the equations are pretty simple. You just kind of have to organize things. Really, only two real equations that you're going to use a little bit in conjunction with each other on this. First one here, you have a toaster oven. Things that produce heat tend to have a high power rating. They also tend to have a high resistance because they're trying to build up and more friction, more heat. If you equate that to when we talked about friction. So my power here is 1050. Okay, my potential difference is 120 volts, pretty standard for a household outlet. What is the resistance? Now, P equals IV, you can't straight go to it. Now, you could do a little substitution, or you could just use two different equations. Okay? So if you use the power equation, you got 1050 times 120, and your flow rate, your current, would be 8.75 amps. Now, I need to get the resistance. Well, you have V and I. Right away, you should start thinking of V equals IR. So 120 outlet, 8.75 amps are going through it, times your resistance. And the resistance you should find is 13.7 ohms. Small electronic device. Okay. And these power ratings are everywhere. So if you look at the back of, say, your cell phone, or you look at the back of your computer or calculator, that's typically what you'll see electricity measured in as far as a consumer goes. So the power is 0.25 watts. Okay. Your voltage is 120 volts. What is the resistance of this device? So same problem, just some different numbers. So PIV, so you got 0.25 watts. I times 120. The current, the flow rate, okay, very low, 0.002 amps. Remember, that's coulombs per second. V equals IR to get to my resistance. So 120 by 0.002 times the R, and the resistance for this little device would be 60,000 ohms. Again, high resistance, going to choke out that flow rate. A lot of speed bumps, a lot of kinks in the hose, slowing it down. All right, your calculator is a 0.1 watt. Oops. It has an internal resistance of 22 ohms. What is the potential difference? Okay, in other words, what size battery does it need? All right, now you could use that substitution and use P equals I squared times R. Okay, that's probably the easiest way to go forward because I don't have my current, I don't have my voltage, so I can't use Ohm's law right now. And so I'm going to use P equals I squared R. So 0.1 I squared times 22. Make sure you take the square root when you're all said and done, because you just want I. You get 0.067 amps. Now to get to your voltage, you have I and R. So Ohm's law, 0.067 times your 22, and you get a 1.5 volts. And any of your cylindrical batteries, your AA, AAA, those are all 1.5 volts. All right. Electric heaters operated by supplying a potential difference of 50 volts across a wire of total resistance. So that's like your little wires that you see in the toaster oven or your toaster. But any heating element is, a metal filament that gets really, really hot. That's an incandescent light bulb's the same way. And you'll see it glow because it has such a high resistance. So 8 ohms, find the current in the wire and the power rating. All right. So I have V and R. I'm going to go ahead and use V equals IR to find my current, and then we'll find the power rating secondly. So 50 volts times my current times 8 ohms, and the current should be 6.25 amps. All right, find the power rating that you would see. So 6.25 amps times your 50 volts, and you'd see a power rating of about 312.5 watts. Now, what would the current in that be if it created a short circuit? In other words, something happened and it bypassed those filaments and your resistance practically dropped to zero. So what's going to happen to your flow rate? Hopefully, if the resistance goes down, the flow rate should go up. So you're going to see a much larger current. So it's still the same voltage. It's just now I have a different resistance. So 50 I times 0.1, and you get 500 amps, which could cause some issues, and we'll talk about that later. But you can see the big difference in the flow rates when you have a short circuit, almost no resistance whatsoever. Now you're going to be looking at kilowatt hours. Your power company charges, if you look at a power bill, electric bill, you'll see this kilowatt hour. Okay. Now, kilowatt is just taking your watts. Watts is a metric unit, so it's just the kilowatt. So once you find the power of your device, say your microwave or whatever it might be, all you're going to do is multiply it by the time that you're using it. So if you used it for half an hour, I would multiply that by 0.5. And that's how you get your kilowatt hours. Now, this isn't a real scientific term. This is just a term, a calculation the power companies use. So you take the power rating of your piece of equipment, whatever you're talking about, you multiply it by the time in hours that you're using it, that it's on. And then what your power company does is set a rate, maybe 10 cents a kilowatt hour, 5 cents, whatever your electric company is charging. And that's how you would figure out how much that device is actually costing you to run. Now, it is relatively low, but if you look at a power bill or an electric bill, you'll see that there are a lot of extra charges, transmission, taxes, environmental charges that greatly increase your electric bill. But kilowatt hours is not so much a scientific, calculation. It's just more of a way that the power company, electric companies use to calculate how much energy you're actually using. So you look at the power, or you could calculate it. So a lot of times, you go to and buy a microwave, they're typically about a 1200 watt, or you look at a 60-watt light bulb. But again, you have to be using kilowatts, multiply the time, say your light bulb is on per day, per month, and then multiply it by the rate that the electric company charges you. And again, I'm going to have a worksheet with some tutorials and a couple practice problems for you to figure that out.